Hello, thanks for joining me in this talk to learn about this very powerful data analysis tool, something that I think you'll find will be very good for taking your data and empirically turning that into something very useful. So this is who I am. I'm an environmental engineer with a background in environmental science and chemical engineering. My specialty areas are wastewater treatment and phosphorus resources. But statistical modeling kind of has a very broad application, so I brought that to many different areas. The outline of this talk, I'll talk about some of the different options that I want to compare to, specifically artificial neural networks. Then I'll describe this approach, response surface analysis, using multivariate polynomial regression, or MPR. I'll show some of the graphical and logical properties of MPR. I'm going to give one example using TaylorFit software to model the property behavior of the strength of concrete as a function of its mix composition. I'll mention a second application, but I won't go into detail in tungsten flow in the economy, just to mention that this has this capability to do what is known as time series analysis, also called nonlinear autoregressive moving average with exogenous variables, the acronym for that being NARMAX, or probably closer to what I do with this software is VAR, or vector autoregression modeling that can model processes. So here's the general problem. What do you do in this situation? When you have some system that produces some kind of output, the dependent variable, but there are some number of independent or causative input variables, more than one or two. So this happens quite often. The example I'm going to talk about is concrete strength depends on how much water, cement, fine aggregate, coarse aggregate, polymer additives, and other factors go in to give you that strength. So we could do many experiments at all different levels of that mix and come up with a data set. But we want to turn that into something easy to use and analyze in mathematical terms. My time series example looks at flows of commodity, in this case tungsten waste, in U.S. economy. And there are about 16 causative variables, but to mention just a few, it's how much we import of ammonium paratungstate, tungsten carbide, and tungsten scrap. And what makes it a time series is you look at not only, these happen to be annual data, but we found correlations between data for those and other flows from previous years. So that's what makes it a time series model. As I said, NARMAX or a vector autoregressive model. In chemical applications, since it's a statistical system that's totally empirical, this has many applications. In chemistry and chemical engineering, it could be used for structural property relationships or physical chemical property correlations, model-based process control. But any field could use this type of analysis, such as biological systems, agricultural plant growth prediction based on numerous variables that affect that, even sociological systems where we don't have even the start for causative, fundamental, mechanistic models, or even where you do have mechanistic models like physical systems. I had someone use this to correlate a lift for a military naval helicopter system based on rotor pitch and speed and air pressure and temperature and so on. So you could collapse data from a table into a very simple equation, made it a lot easier for him to predict the performance of his machine. So if you have data of this sort, this multivariable input-output data, what can you do with it? How can you come up with a model or a relationship for it? I think most people are familiar with multilinear regression. It's a widely available tool. Many are also available nowadays with artificial neural networks, which has quite a better capability, but has certain disadvantages. And what I'm proposing here is multivariate polynomial regression, which has almost all the advantages of both of these, and also avoids most of the drawbacks of both of them at the same time. So to inform people about what artificial neural networks are, it's really a classic black box model. Multiple inputs, single output. There's something going on inside. I won't get into the details here, but it does have advantages of being able to produce very accurate fits, can describe very complex behaviors, and I'll describe what I mean by complex behaviors soon. One thing it's good at that might be even better than what I propose is it can handle very high dimensional problems like image analysis. But it has a problem that the model itself is complex. It makes it hard to analyze. You can't take the derivative. You can't communicate it. People publish it without, they just give the results in terms of how it performs without publishing the model itself. But it has a huge number of coefficients hidden under inside that black box, which makes it susceptible to overfitting. And you don't really know how and why it's producing this behavior. So it really is a black box. What I am proposing is multivariate polynomial regression. People have seen something like this before, in response surface methodology. This is not quite the same thing. Multilinear response, multilinear regression describes an output as just a linear combination of your inputs. If you have two inputs, X and Y, you get two sensitivity parameters. So the sensitivity of your output Z versus one of your inputs, X, is just a single constant. The slope does not change. But what if your data has slope that does change when Y changes, the second variable? That's a classic interaction. And people are familiar with how to handle this. You can add in an interaction term, the product of X and Y. Now you add to your sensitivity a term that's a function of Y. Well, what if your data is curvilinear and also shows interactions? Well, here's where the polynomial, multivariate polynomial comes in. We could put in terms like x squared y cubed, even x divided by y. And then you can get more complex sensitivities going on in there. But if you're examining data with nonlinear relationships such as these, and your data have those behaviors, but you don't test for them in, say, a multilinear regression model, or even multilinear regression with interactions, or even a polynomial model where you've kind of restricted the kinds of variables, you're going to have a biased model, or you have the potential for a biased model. You have to check for these kinds of possibilities. So here's a graphical approach to what you can do with more complex surfaces. So first of all, this is a multilinear model. It's just a plane in three-dimensional space. And here's only two inputs. The interaction term gives you this kind of saddle shape. And we can get into more complex shape. XY squared is kind of a twisted surface like this. X squared, Y squared, even more complex. And each of these surfaces is a different behavior from the others. Here's X times Y cubed. Each one of these is unique. With multidimensional data, especially if they're more than two independent variables, you can't visualize these surfaces. You have to look for these analytically. Here's, if we include ratios, we can get saturation type phenomena, which is common. I mean, saturation behavior is commonly observed, especially in chemical processes. So we get, again, response surfaces that can be quite complex. So this gets into the complexity here. Now when you get into 3, 8 variables and so on, and you get these kinds of relationships among parameters, this is really complex. This is the essence of what when a scientist or engineer is asked about how the behavior of a system and says, well, depends. It's complicated. It's complex. Well, this is it. What the response to one variable depends on another in a nonlinear way. Well, how do we tease that out? Another thing to illustrate the power of polynomials is their logical capabilities. And I studied this because the older neural networks were limited in their logical capabilities. So I want to test polynomials and realize that they also could handle complex logic. So here are some polynomial functions to represent each of these basic logic functions where we express true as 1 and false as 0. if an output is not A, then that output is just 1 minus A. Exclusive OR is A plus B minus 2AB. Right? So down below you have the truth table for exclusive OR, which we can kind of interpret as either or but not both. But we can go beyond just two independent variables. And you notice that exclusive OR, as well as the OR, requires an interaction. But supposing you had a more complex logical relationship like this one, with three inputs, A and B, exclusive ORed with not C. Well, here's the truth table for this logical relationship. And how can we find out a polynomial that fits this? Well, we just have to put it in, extend the table to form these interaction terms, and then just do multilinear regression against all those columns. And the coefficients give you the parameters of your polynomial. In this case, it's that logical relationship is expressed as y is 1 minus c minus a times b plus 2 times a times b times c. So there you have it. And you could simply change that y column to create any logical relationship, any truth table, and it will come up with the polynomial instantly that corresponds to that logical relation, that truth table. Well, if we allow, now in this case, three independent variables, and we allow polynomials of higher degree up to degree 2. So you can see here's a multilinear model, pointed to there. Here are some interaction terms. Here are quadratic terms, univariate. But we could look at terms like q squared r, as I mentioned, or r squared q, or qr squared s, all the way up to q squared r squared s squared. So in this case, there are 27 possible terms, but all of them might not be statistically significant. We only want to put terms in the model that contribute to the model, otherwise you have the potential for overfitting. So I have an algorithm to limit model complexity. We use stepwise regression. We look at the terms, we set our number of exponents, our number of multipliers. If it's a time series, we include lags. Generate candidate terms. Check which are significant. Add one to the model. If any are currently in the model are not significant, we take them out. You'll see how this is done very easily. Generate a new list of candidate terms of using the terms not in the model added to the current model. Are any of them significant? We repeat this. If not, we add more parameters. When we've gone through this whole thing twice, if we cannot improve the model by adding significant terms or removing any term, then you stop. So it converges absolutely. So I'll show you the example, but you get this complex response surface in n space. It can give you accurate results, as accurate as neural networks, but it's transparent. You get a simple, compact equation. It's transportable. You can put it into a computer program. You can publish it. It tends to be unbiased, especially if you use something called cross correlation that I'll mention later. Very tractable. You can differentiate it. You can plot it. Resistant to overfitting both because you can cross correlate and because you keep out the terms that are not significant. In contrast with neural networks, where you don't know which of those coefficients really are important for the fit. So this has been implemented in an online client-based software that runs directly from your browser. It's free. You go to that website and you're there. So let me show you how this works very quickly. There, you're in the software. You can open a user's manual. You can download some data files that I've given you for playing with. I'm going to import, as I mentioned, this concrete fitting data file. So I'll open that. And the program has these three areas that if you mouse over, it kind of expands. And at the bottom is the data set. And it shows the columns. It's just, and this shows you what the data requirements are. Anything that you could fit into basically a spreadsheet. Columns and rows with numeric data. where one column depends on the others, you can analyze it with this. Here, I want to select my data column is over here, that my dependent data column. I'll mark it as the dependent. And these other columns are the independent variables, the causative variables, the content of cement, slag, fly ash, water, superplasticizer, coarse and fine aggregate, and also the age at which the concrete is cured. Up above, this pane shows the current model, which always starts out with nothing more than an intercept term, a constant, which is basically just the average of the dependent variable. And it gives the variable, the coefficient associated with that term, the associated t-statistic, and the probability of a larger t. And as long as that probability is less than a criterion, usually 0.05, we consider this a good fit. We also have global goodness of fit statistics, such as my R squared or adjusted R squared, the F statistic, and the probability of the F. I've plotted my residuals here. Right now, there's only one, the residual versus predicted variables. Since it's a constant model, there's only one predicted variable, so it's aligned vertically. Now let's add to the model. Right now, over here, we have terms not in the model based on certain settings, which I'll get to later. But right now, it's looking at only linear terms like a multilinear regression model. I'm going to sort on T by clicking on it. And the strongest term with the largest t-statistic is superplasticizer. I click on that. The terms that are significant are highlighted in green. So I can pretty much go through and just click one after the other, adding everything with green. But I got to keep an eye over here, because if the probability turns to red, it means it's crossed the threshold to non-significance. At this early stage, I'm going to not remove that yet. At some point in the future, I will be a little stricter. But let me put in a couple more here. And fine aggregate, coarse aggregate doesn't seem to have an effect here. So I'm good as a multilinear regression model. My adjusted R squared 0.63. Right? And I've got pretty good scatter, no obvious bias here in my residuals. Now I'm going to show you how to do cross correlation. Basically, I input a separate independent data set with the same columns. And the current model, t-statistics and coefficients are always computed using the fit data set. And I have the global statistics for the fit data set here, but I also compute global statistics for my cross correlation data set. So slightly lower adjusted R squared shown here, slightly lower F statistic, and but still very strong models. Now here's where this really comes into play. So first of all, I'm going to expand the number of the kinds of terms I'm going to look at. Instead of just multilinear, I'm going to put in multiple hands up to 2, which means I can look at variables cross-correlate the interaction terms. I'm going to look at some global goodness of fit statistics. I can choose from any of these. I'm just going to pick one now to make things simple, the adjusted R squared. Right, so that shows up there. And now look, it's including terms that are interaction terms like superplasticizer times age. Also, some of my linear terms that I didn't put into the model before are still here. I have to look at other pages here. Fine aggregate by itself is there. I'll go back to page 1. I'm adjust on the adjusted R squared, and I will add terms to the model only if they have statistically significant t value and an adjusted R squared better than the current cross-correlation data set has. So when I see these 2 greens, I'm good. I add that in. It shows up over here in my model. And I'm going to put in a few of those. And what happened? Now, back over here, superplasticizer wants to come out. There's still superplasticizer in the model, but interacting with age. But by itself, it comes out. And I can keep going, add a few more. Interesting, I added that in. That looks like that didn't help. I need to take out my intercept. I at this point. And I'll add a few. I could keep going. It doesn't like that one. I'll pull that one out. Fly ash times superplasticizer. Nope, it's not a good one. So oh, I'm sorry. None of these have a good T. That's why it showed up as red when I crossed it over. So actually, I should stop with these sets of parameters. Now comes the real power. I can add in my quadratics by putting in exponents of 2 as a candidate exponent. And I'm going to jump ahead and put in a -1, which allows the model to look at ratio variables. And this allows those more complex shapes to show up. Again, I'm sorted on adjusted R squared. I've got a strong T for 1 over fine aggregate times 1 over age. And I will add a few of these. Slag comes back in. The ratio of slag to age. I'm going to go to the second one here because it's superplasticizer squared divided by the cement content. So I put it in. And I could keep going. I'm not going to go all the way just in the interest of time. I have a very strong model here. R squared is already 0.8 in my cross correlation file. Pretty random distribution of errors. I can take some code that I can cut and paste and put it into a program or an Excel file and so on. Very powerful. So back to here. And I will try to conclude this talk. My flow of tungsten model, this is the time series model. I modeled this single flow in this flow diagram. This shows mining, food production, manufacturing, use, and disposal. Again, you have a spreadsheet type of data set, but here, let me jump ahead. You're modeling now, in this case, flow 10 versus all the previous flows as possible predictors from previous years. How does last year's flow, or even 2 years' flow of mined ore affect this year's waste production? So if I fit to it, the linear model, not a bad fit, but the MPR model, or really this is now a vector autoregressive model, very high precision. R squared goes from less than 0.4 to better than 0.96. And I got a kind of complicated function here, but you know, you don't want to look at individual terms. It's like looking at a cubic equation and say, just looking at the quadratic term by itself and saying, what does it mean? That's not how to look at it. You want to look at the overall shape. But this has individual terms that will be familiar, like a linear term, a multilinear term. Here's an interaction term. Here is a quadratic term with interacting with another variable. And here's a ratio, F2 at K minus last year divided by F flow 8 from 3 years previous. So, and you can take that equation, you can look at it with the data and show how you get interactions graphically, hold some parameters constant, look at sensitivities, and so on. So, MPR can identify very complex or even chaotic behavior. I didn't describe that, but I have references that can explain, show that capability. If you do not consider nonlinear relationships such as these and they exist in your data, then you have a possibly biased model. You really should dust off the data and do that analysis again. So data are more valuable in computations. If you used multilinear regression in the past, reanalyze. If you used neural networks, you might get some more out of it by looking at the same data this way. What you have to do is just go to that website and you're done. So thank you. These are several papers describing with some more details about the applications of this model. Thank you. Vielen Dank.